Welcome everybody to the second day of our Escola Brasileira de Sistemas Dinâmicos. It's a great pleasure to welcome all of you here at IMPA. All the activities from now on until the end of the week will be held here at IMPA. And it's a pleasure to introduce Balázs Bárány from Budapest University of Technology and Economics. And okay, he will talk about fractal geometry and the transversality method. And according to what Catherine told me, the background of the poster apparently is a blackboard of Balázs. And
so you can expect the worst.
So it is essentially about the same topic of the mini course. Thank you.
Yeah, thank you very much. First of all, I would like to thank for the invitation. That's my very first time in Rio, and I really enjoy it. It's a fascinating place. And also, so I would like to talk about this fractal geometry method called the transversality. And I tried to find some kind of, a big machine gun which can kill all the known transversality results at the same time, but in weeks of preparation I had to realize that there is no such kind of thing. So I cannot call it transversality theorem, I can call it only transversality method. Because there are always some kind of nice sophisticated modifications which are required for several kind of different problems. But I also want to give you now a very, very introductory thing from the very basics. So I'm pretty sure that what I will tell you in the upcoming 45, 50 minutes, most of you are very much familiar with, and then you can enjoy my voice as some kind of background noise. You can do this anyhow. So, okay, so in every workshop, in every school, there must be a poor fella who introduces and defines Hausdorff dimension, and since no one did it yesterday, I will do it today. So the first thing is the S-dimensional Hausdorff measure is the following object. It's HS of some subset of E. E is some kind of complete, X is some kind of complete metric space. It's usually in RD. And it's the supremum over all deltas, such that you are trying to cover in the most efficient way your set E with other sets, UI. So you are covering it. This is a countable index set. And you also assume that the diameter of these sets are delta. You take the most efficient cover, and then you take the supremum in delta, and this will be the S-dimensional Hausdorff measure. Of course, it can be defined for every set. There will be an outer measure, but this is nice Borel. So on the Borel sets, it will be a nice Borel measure. So what is the Hausdorff dimension? So this measure has this interesting property that at certain value it jumps from infinity down to 0. So the Hausdorff dimension of the set E is the smallest value of S for which the S-dimensional Hausdorff measure is 0. Okay? Oh, yes, exactly. So U means the diameter of U, which means the supremum of the distances, whatever the distance now is for every set, for every points X and U. Yes. And whatever happens at this value, it can be anything. It can be still the Hausdorff dimensional measure still can be infinite, can be 0, can be something in between. Anything might happen. Which one? Yes, it jumps from the infinity to 0. Oh, so in the following sense, you begin your journey at from 0. Here, it's infinite. Then it happens something. Anything can happen. And then this jumps down to 0. So this is the S-dimensional Hausdorff measure. OK. And it has a very nice characterization using measures, which is the so-called Frostmann's lemma. Usually people tell also at this stage the mass distribution principle, and basically from the mass distribution principle you can prove Frostmann's lemma, at least in one direction. I will just ignore it. Okay, so I will just state Frostmann's lemma and won't prove it. But this is very useful for us, and it says the following. So if mu is a Borel probability measure, such that it gives positive mass to my set E. And what I also see is that the S energy, it's the same E, it shouldn't be the same E, so it should be a calligraphic E. The S energy of my measure mu, which is the following double integral, integrate x minus y to the power minus s, and integrate it over d mu x and d mu y. And what you see is that this energy integral is finite. Then it follows that the Hausdorff dimension of E is at least this value of S. No, it's all everything. You integrate over everything. The only thing what matters is that it gives you positive mass to the set E. So if you restrict yourself to the set E, it will be still finite, right? So it's something overestimated. Yes? Oh yeah. We are still in in this complete metric space. So E is still, well, feel free always to think about RD, because that's the easiest. But since we have a complete metric space, we have Borel sets, everything. So it's a nice and charming, friendly word. And this Frostmann's lemma is almost if and only if. What do I mean by almost if and only if? If what you know is that the Hausdorff dimension of your set E is strictly greater than S, then there exists a mu Borel probability measure such that it gives positive mass to my set E, and also this S dimension, this S energy of my measure mu is finite. So if you are happy to have some kind of little epsilon errors here, then it's basically an if and almost if and only if result. But this energy integral is good to characterize the Hausdorff dimension of sets. And also, if we have Hausdorff dimension for sets, why shouldn't we have Hausdorff dimension for measures? And there are two nice definitions for the Hausdorff dimension of measures. The one thing is that, okay, from this you can clue that if I have my set E, its Hausdorff dimension should be the supremum of such kind of measures, right? Where the S energy integral is finite. So let's define in this way. So if I have a mu Borel probability measures, well, I like my measures to be probability measure. You can have have locally finite measures, but in my world, the probability measure is the nicest object. So if mu is a Borel probability measure, then you can define the Hausdorff dimension of the measure mu as follows. Take the supremum of the Hausdorff dimension of the sets such that, take the infimum. Of course, the full set would be always there. So the infimum of Hausdorff dimension of what sets? Because there are two options, right? Either my set here has positive measure, but also I could say that I define the Hausdorff dimension over sets which has full measure. And this distinguishes between the lower and the upper Hausdorff dimension. So I will define also the upper Hausdorff dimension for measure mu as being the infimum of the Hausdorff dimension of those sets who has full measure, so whose complement has zero mass on it. Okay, so somehow you can understand, you can introduce these quantities via some kind of global picture. What is the smallest set which is still visible by this measure, or what is the smallest set which is completely visible by this measure. But also, you can introduce this in a local aspect. Namely, so this is the lower and upper Hausdorff dimension of my measure mu. Okay, this is a definition. This is also a definition, let's say. The local dimension. So for any point from my space, I can define the lower and upper local dimension of the measure mu at this point x by taking the lim inf and the lim or the lim sup of the measure of the balls at this point x with radius r. How fast does it shrink? By the way, this symbol here confuses usually people. This is my sign for logarithm. Okay, so this is always the logarithm. No one has time to write down the O, and especially these redundant double O's. Okay? So this will be always my logarithm. What is the base? Your favorite one. Okay? I will divide always logarithm into logarithm, so it doesn't matter. So what you are interested in, how fast is radius measure of a ball shrinks down to 0. It might not shrink down to 0 if my measure is atomic, right? So it can be 0, very well, but it can be also infinite if this point x is not in the support of my measure by just simply defining the 0 of the logarithm being minus infinity. Okay, so it can be between 0 and infinity, everything. But this is for every point. For typical points, this behavior is quite nice. So if you are saying that you are interested in what is the essential infimum with respect to mu of the lower local dimension of x, this will be exactly the lower Hausdorff dimension of the measure mu. And also you can define the essential supremum over almost every point, essential supremum of the lower local dimension again, which will be the upper Hausdorff dimension of my measure mu. So this object is the local dimension of mu at x, and this is the lower and upper Hausdorff dimensions. How you can show this? It's quite easy, and you can use this Frostman lemma, combining with the following lemma I will tell you in a minute. But it's very useful because we can understand the dimension of the measures, and especially the dimension of sets, via understanding the typical local behavior of this measure. And you can ask, then, what is the upper local dimension is good for, right? Because upper and local. Upper and lower. Well, the upper local dimension is good for the so-called tricot or pucking dimension. However, during this talk, I will ignore that. If you would like to know more about this, I recommend Falconer's Fractal Geometry book, which is a very excellent book and very, very good for beginners. Okay. Sorry? Here? Yes, so this must be also, although we took the essential supremum, it's still, we consider the lower local dimension. So the upper local dimension gives you a completely different dimension concept. Yeah, and what is the relation then of the local dimension here with the Frostman's lemma and its energy estimates? Well, it is this very nice connection, lemma, in the essence of Frostman. If you see that the lower local dimension is at point x is strictly greater than some value s, then if you integrate the x minus y to the power minus s with respect to mu, then this will be a finite integral. And also, vice versa, it's almost again, if and only if, because if this integral, which is, you see the inner part of my energy integral, if this is finite, then what I know is that the lower local dimension of x must be at least s. Sorry? Oh, yeah. Thank you very much. First integral with respect to y. Yep, exactly. Thank you. And the proof is very, very simple. And to finish the proof, it's homework. So if you look at this integral minus s d mu of y, then you can write it as an integral from 0 to infinity, the mu measure of those y points such that x minus y to the power s is greater than r, dr. And what is this guy? This guy is basically that x minus y is at most r to the power minus 1 over s. Right? From this version, you can easily write and prove this lemma. And then it's also visible why this energy is related to the lower local dimension of these sets, the lower and upper Hausdorff dimension. Okay? So these are the very basics which we intend to work with. Yeah, maybe are there any questions? Okay, so it is, since it is quite an introductory course, I would like to present you one of the most basic results in fractal geometry, in the geometric measure theory, and which is the projection result of Marstrand. There are two good reasons for that. That paper of Marstrand from 1954 was extremely influential. So it's good to know if you don't know what Marstrand's theorem is. My other option is everybody in his life, every mathematician in his life should see the proof of Marstrand theorem at least once. So if you have already seen it, then spot my mistakes. That's a good game. If you haven't seen this, then spot my mistakes. Then it's still to make you the amusement double. And also, why I would like to present it, because this is really the precursor of this transversality method I intend to talk about. So what is this Marstrand's theorem I'm talking about? Theorem of Marstrand from 54, I think. It says that now we wander to the plane, right? This is, up to this moment, it was very general. Now we go to the plane. So let E be a Borel subset of the plane. Actually, it's true for analytic, but our word being Borel is good enough. Okay? And let's define the orthogonal projection from R2 to R be the orthogonal projection from R2 to the line with slope tangent theta. Okay? So theta is coming from, let's say, 0 to pi, or 0 pi would be right enough. Okay, so we can simply formalize this function as well. xy being, okay, cosine of theta x plus sine of theta times y, right? Very basic, very simple. What Marstrand says is the following. For Lebesgue, almost every direction theta from 0 pi, if you look at the Hausdorff dimension of the image under this projection of your set E, then this must be what? The minimum of 1 and the Hausdorff dimension of E. Furthermore, if this Hausdorff dimension of my set E is strictly greater than 1, then for Lebesgue almost every direction, the Lebesgue measure of this orthogonal projection is positive. First of all, why is this minimum of 1 and the Hausdorff dimension of E? Well, it's not hard to see that the real line must be a one-dimensional object in any reasonable dimension. And your dimension cannot be, if you are inside of some kind of set, your dimension cannot be larger than this set, right? So the dimension in this sense must be monotonic. So for every A and B, the Hausdorff dimension of A cannot exceed the Hausdorff dimension of B. This is why this 1 is here. Why is this Hausdorff dimension is here? It's because the orthogonal projection is clearly Lipschitz, right? So we also know that no matter what the value of theta is, if you're looking at these distances, this is at most the distance of x and y. So basically, if I want to use the definition, right? If I use the definition of the Hausdorff dimension and I'm covering my set E, its images will be also serving as a cover for my set. So for Lipschitz maps, the Hausdorff dimension cannot grow. So the projection for any this is true for any Lipschitz map. Under Lipschitz maps, the dimension cannot grow. But of course, it can decrease. For example, if I'm on the plane, a very easy example, here is my line segment. And of course, if I project it down to the x-axis, I will get one single point. Right? But this is only one point, and among many others, when I still see in the projection an interval. So the big thing in Marstrand that essentially for typical choice of projections, you don't see dimension drop. Namely, your dimension value is as large as possible. Okay? And of course, there is a measure version for Marstrand's theorem, which is the theorem of Hu and Taylor. Can I erase the first two boards? Thank you. So this theorem is due to Hu and Taylor, which is the equivalent version of the projections of measures and Hausdorff dimension. And for simplicity, I will state that again only on the plane. Okay? So this is a special case of the theorem of Hu and Taylor. And again, let mu be a Borel probability measure on the plane. Then the Hausdorff then for Lebesgue almost every theta, the upper and also for the lower Hausdorff dimension of the projection of this measure is the minimum of 1, and the upper and lower Hausdorff dimension of my original measure. This means the push forward. Okay, so this is from set A, the mu measure of its preimages. Okay, and also, just like there, if the lower Hausdorff dimensions, you have to be careful in this sense, the lower Hausdorff dimension is strictly greater than 1, then the Lebesgue almost every theta, this measure will be absolutely continuous with respect to the Lebesgue measure on the line. Okay, so we are going to prove this special case of Hu and Taylor. But these orthogonal projection results has been generalized in many, many contexts, like Matilla, the 70s, extended for orthogonal projections from RD to k-dimensional subspaces. Then Kaufmann and Falconer gave estimates on the exceptional directions. So these estimates here are saying that the exceptional set of directions where I see dimension drop, so the dimension value is strictly smaller than its natural upper bound, has Lebesgue measure 0. They also estimated, Kaufmann and Falconer, the exceptional set, Hausdorff dimension. Basically, for the planar version, they result saying that the Hausdorff dimension of those directions for which it is strictly, the Hausdorff dimension of the projection is strictly smaller than the minimum of 1, and the Hausdorff dimension of E is the minimum of the Hausdorff dimension of E and 2 minus the Hausdorff dimension of E. So this version is still stated on the plane. There are also higher dimensional versions coming from Perez and Schlag. Okay, and this is also a quite active part of research, doing projections from restricted domain. So, for example, you are projecting R3 objects on lines, but you are not considering all the lines from the projective sphere, just some kind of curve. Okay, so there, this is still a quite nice active field. Okay. So let's see what's going on, and let us prove this theorem. Okay, so what do we want to show? Again, because this orthogonal projection is a Lipschitz map, then the dimension, not only the sets, but the dimension of measures cannot also grow. Both the lower and upper cannot grow. So what I want is to show that, let's say, both the lower and upper dimension is greater than the minimum of that value. So let me call alpha as the minimum of 1. And I will cheat a little bit because I will prove simultaneously both cases for the Hausdorff dimension. Okay, both cases simultaneously. Why? Because what we want now to show that the orthogonal projection, the lower and upper, is greater than alpha minus epsilon for almost every theta. Right? And then letting epsilon goes to 0, taking this big intersection along epsilon along some countable set going to 0. So it's fine. So what do we need? The lemma says that the Hausdorff dimension is strictly greater than alpha minus 1, almost if and only if I'm looking at this energy integral, this is alpha minus epsilon, I project it down, my measure, right? Okay, so if, at the moment this is just one integral. So if this guy is finite, then I would know that the local dimension at x is at least alpha minus epsilon. What do I need to know? For typical cases, right? For typical x's, it should be finite. So if the integral, if I restrict my measure to some set A, this is finite, then I still know that for almost every point in mu, the local dimension is at least alpha minus epsilon. Now it's a matter of how you choose your set A. And if you work with the lower Hausdorff dimension, choose the set A to be positive, and such that in mu you see that this double integral of x minus y minus alpha minus epsilon, so this integral, oh my god, I'm running out of space. Oh, there's a plenty of space. Why do I write there? So if you're working with the lower Hausdorff dimension, then choose A in such a way that it has positive measure, and this double integral x minus y minus alpha minus epsilon d mu x and d mu restricted to set A, y, this is finite. And it's possible to do because the essential infimum is strictly great, is at least alpha. So I decrease a little bit, I must find some positive measure set. And if you are working with the upper Hausdorff dimension, then choose A in such a way that its mass is almost 1 minus epsilon. But if the upper Hausdorff dimension is at least alpha minus epsilon, then again, you can choose such kind of set. A with almost full measure, where this integral is finite. Is it okay? If you have any questions, please don't hesitate to interrupt me. Okay, so what we need is that to show that for almost every theta, this integral here is finite. It's usually very hard to show. It's easier to show usually that something's expected value is finite. No. For every epsilon. So I just say that I fixed my epsilon, and for this epsilon I will use this set. Yes, this set A, and for every epsilon I re-choose my set A. Thanks, that's a very good question, thank you. So now we want to show that this is finite, and instead of that we will show the stronger thing. We will show that if we integrate it from 0 to pi, this will be finite. If this is finite, then we know that this energy integral is almost surely finite. If this energy integral is almost surely finite, then this variant of Rossmann's lemma provides a slower bound for the dimension. Okay. And if I see two integrals, I want to figure out whether it's finite or not, but I don't know one version, then I immediately apply Fubini, right? Fubini like a lunatic. So what do we do? First of all, I don't like this version. First of all, so I call this I, okay? Just to call it somehow. Okay, first of all, I move the double integral outside and the Lebesgue integral inside. And also I want to apply the definition of the push-forward measure. So I'm integrating p theta of x minus p theta of y. Right? Otherwise I could not apply Fubini at all. To alpha minus epsilon, integrated by d theta, mu x, d mu restricted to a y. Okay? And then the next step is integrating from 0 to pi. Actually, no, the next step is the following. I introduce here the distance of x minus y to the power minus alpha minus epsilon. And then here's an integral from 0 to pi. And now let's use that the orthogonal projection is a linear guy. So what do we integrate here? The p theta image of x minus y divided by x minus y absolute value to the power minus alpha minus epsilon. Here is an integral of d theta, d mu x, d mu restricted to a y. And now I think you see the strategy. The strategy is to show that this middle integral is what? Is finite. Because if this middle integral, this is what we need. If this middle integral here is finite, then we are done, right? Then what you see here, this is exactly your choice of the set A. Okay. Yeah. So and also, you might say that I was dividing by 0, but of course I was dividing by 0 in a zero measure set, so it doesn't do anything. So what we need then? We need that this is finite, so which means that for every v, actually we need a universal constant, right? We need a constant c. Not only that's finite, we need a universal constant. We need a universal constant c such that whatever we choose however we choose the vector from the unit circle, if I integrate from 0 to pi the p theta v to the power anything, and here it's a different beta, but beta will be smaller than 1. That's all its property, right? This alpha is definitely strictly smaller than 1 because of this minimum. So I claim that for every beta, there exists some kind of c, depending only on beta, that no matter how you choose your unit vector, this integral here will be finite and at most c. And this is why I showed you the trick how to prove this local dimension formulas for the Hausdorff dimension of measures, because you can apply here exactly the same. Right? So I'm integrating this guy, the power minus beta, and it's an integral from 0 to infinity of the Lebesgue measure. Don't forget, this Lebesgue measure comes from 0 pi, such that p theta of v minus beta is strictly greater than r, dr. And this guy is, again, that the orthogonal projection of v is at most r to the power minus 1 over beta. Okay, and for small r's, right, this number here is horrendously large. But I'm integrating on a finite interval, so I'm interested in what is the decay. So I will only integrate from 1 to infinity, okay? So the same Lebesgue measure, those thetas for which theta of v is at most r minus beta dr. Again, I'm only interested in the decay. So, which means that I want to measure the set of directions for which the orthogonal projection of v is small. But observe one thing. Right, so if you look at the formula, so it's cosine of theta v1 plus sine of theta v2. What happens if we take the derivative? Well, nothing. v1 plus v2. Right? What is the interesting part here, that if I take the square of both of these guys, then what do you get? v1 square plus v2 square, which is uniformly 1. What does this mean? There are not only no double roots, you can pretty much handle how many roots are there on this interval, right? Because this formula also says that if I have a direction, theta, for which this orthogonal projection is very small, let's say strictly smaller than 1 over square root of 2, then I also know that the derivative of this map will be strictly greater than 1 over square root of 2, otherwise they cannot sum up to 1. Right? So this is the picture here. This is the interval 0 pi. This is the 1 minus 1. This is the minus 1 over square root of 2, 1 over square root of 2. Right? So this is the region when my function enters. So this is theta, and this is p theta of v. This is the region where if my function enters, by the way, it's 50, but can I still be, okay. So when my function enters, then its slope must be at least 1 over square root of 2. Also, you know that its slope, the slope of this function must be at most 1. So what you see here, that here, this function goes through with more or less a constant speed. Right? And then it can turn back very quickly, but again, needs to go through on it with more or less of constant speed. So if you have a root, it is not a double root, it's a simple one. And you also know that there is this uniform neighborhood where it behaves very nicely. So this this length of such kind of tour is, I think, at least, what? 1 over square root of 2, because the slope is at most 1. So what does this mean? The number of roots is what? Pi times square root of 2 at most. It's a very big upper bound. So, but also because of the slope, if I'm looking at a tiny neighborhood, and what is the tiny neighborhood I'm interested in? The r to the power minus 1 over beta, right? This is my tiny neighborhood. Then I also know that the side length here is at most 1 over square root of 2 times, square root of 2 times 2, because up and down, r minus 1 over beta. So what do we get? How large is this guy here? This guy here, So this guy here is at most the number of roots, which we see that pi times square root of 2, times this tiny neighborhood of the root, which is, I don't know, square root of 2 times r to the power minus 1 over beta. So you found the universal constant, and the function in r, who is, because beta was strictly smaller than 1, is integrable. So you get that this guy here is finite, uniformly depending only on your pre-chosen quantity. Okay, so because of the lack of time, I will avoid the proof of the absolute continuity, and actually during the talks I will focus only on the dimension. Okay, but what you have seen here is basically the transversality method. These are what you, and this here, when I say that there is this parameter family where there is this quantity, the image of this unit vector. I don't want it to be small, but in time to time it is. So I want to measure how small these directions are where it's tiny. Then what I get is that this is at most constant times r. This is basically the transversality condition in almost any aspects. This is the quantity we are hunting for, and we are using them. More or less almost every proof goes through in the same way, just you need to be careful for the actual situation among technical difficulties. Okay, so I think this is a good time to stop for my talk today. Thank you very much.